conjugate pairs theorem says that if p of x is a polynomial function whose coefficients are real numbers, and if z is equal to a plus bi is a zero of p, then its conjugate, the conjugate of z, that's what this line over means, the conjugate of z, which is equal to a minus bi, is also a zero of p. There isn't really a whole lot to explain the conjugate pairs theorem. Basically what it says is that if we have some complex zero in the form of a plus bi, then it has to have another zero, which is its conjugate, a minus bi. So anytime we have a complex zero, then it's going to come in a pair, like all good things. It's going to come in pairs. That is why when we used our rule of signs, when we found out that, let's say 1, 2, 3, 4, we have 4 variations. We either have 4, 2, or 0. And the reason that we've been subtracting these even integers is because if we have a non-real solution, then its conjugate is also a solution as well. So that's why we've been subtracting these even numbers from our possible solutions. So if we had gotten 5, then we could have 3 or 1. And now you know why the reason that is that's because imaginary solutions or complex solutions come in pairs like this. So let's do a really quick example. Let's suppose I have a polynomial function of degree 5 with real coefficients. With the zeros. That was a backwards Z. With the zeros, let's say 1, 5i, and how about just 1 plus I? Find the remaining zeros. So first off, we need to figure out how many zeros we're going to have. According to the fundamental theorem of algebra, a polynomial p of x has, in the form of an x to the n plus all that stuff, has, oh wait, that's n to the x. Oops. An x to the n, plus all the other stuff, has n solutions. So here we look, and we have a polynomial of degree 5. So we're going to have 5 zeros. And we're already given 3 of them. We're given 1, which is a real number, 5i, which is a complex number, and 1 plus I, which is also a complex number. And what this theory up here has said is that when we have a complex zero, not a real zero, a complex zero, when we have a complex zero, it comes with a conjugate pair. It must have a conjugate pair, and I'll explain the proof of it after. But for right now, just know that if we have a complex zero in the form of a plus bi, its conjugate, a minus bi, is also a zero. So we can go down here and say, here we have a complex number, and here we also have a complex number. So this conjugate pair, or this number must have a conjugate pair, and that would be minus 5i. And this one's conjugate would be 1 minus I. So the two missing zeros are minus 5i and 1 minus I. So our total zeros are 1, 5i, minus 5i, 1 plus I, and 1 minus I. And that's all the conjugate pair theorem says. It's pretty simple to understand, but obviously when we are working with our problems, they're going to be a little bit more complicated. So I'm going to stop this video here, but I'm going to find some complex zeros, much in the way we've been looking for real zeros, except now we're going to include complex numbers. So I'm going to do some of those problems, and I'm also going to attach the proof to this as well.